In this video, we're going to talk about discrete functions and arithmetic sequences. We're going to talk about the terminology related to discrete linear functions and create some equations to model. So remember that linear functions, up to this point, we've mostly used y equals mx plus b and sometimes another form of the equation, but it was still equivalent. You could use either. And we mostly had linear equations that look like this. Nice solid lines, but occasionally we would have certain situations that would give us only dots. We would only have dots in situations where our independent variable did not make sense for non-whole number values or for certain values. So for example, I could be buying t-shirts at $5 each, slopes a little bit off on this, and it only makes sense to buy one t-shirt or two t-shirts or three t-shirts, four t-shirts, only whole number t-shirts. I actually shouldn't put a dot at 0, 0 because it doesn't, I guess you could buy 0 t-shirts for $0. I'm going to define this though as we start keeping track once we're buying something. And a linear function, it wouldn't quite make sense to have a t-shirt and a half. So a continuous linear function wouldn't model the situation very well. These dots, this discrete function would be much better. These numbers that we're using here starting at 1 are called the natural numbers. So we have 1, 2, 3, etc. We use a fancy schmancy capital N with this like double look to it. And we're always going to use the variable n. So let's say n equals, and it basically means that n is a member of the natural numbers. So in this unit, when you see an n, you can assume the values that are possible for n are 1, 2, 3, and other natural numbers. I'd like you to go through the textbook and work on these definitions. A sequence is just a list of numbers with a specific order. So I could have a list of numbers like we had in the t-shirt question, $5, $10, $15, $20, etc. And it's important that they're in order because if I buy one shirt, it's $5, two shirts, it's $10. If I put them out of the order, it would look like I buy one shirt, it's $10, I buy two shirts, it's $20, I buy three shirts, $5. It makes no sense. So the ordering here would make sense, given that the first thing is buying one shirt, the second thing is buying another shirt. We call each of these elements in this list terms. So a term is one of the numbers in the list. So you can see in this series that I've given you, it's always going up by a constant amount. So it's always going up by 5 in this situation. And in general, it looks like our initial value plus 5 for our next one, plus another 5 for our next one, plus another 5 for our next one. And eventually, if we have n t-shirts that we're buying, we could create an equation, and it would be the initial amount plus n minus 1 times 5. So every time I'm adding $5 to that initial one. Notice that it's not n because the first number didn't have a difference added to it. So it's only starting at our second number, t2, it's only then adding a d. And our next one, t3, has two differences, two d's added to it. So always the number that we're seeing that's multiplying the d is always one less than the term number. So that's why by the end, tn is going to have a plus n minus 1. So what I've set up here, that's our general term. It just represents any possible term in the equation. I could sub in the number for n, and it would work out that it would give me the number for the term. It's very much like having an independent variable n and a dependent variable tn. And I can pick 1, 2, 3, And then for my terms, if we use the t-shirt example, I'd have 5, 10, 15, etc. Or just in general, my first term would be a. I add d to that, and I get a plus d. I keep adding a plus 2d, and it continues on. A recursive sequence, that means I can write any term in the sequence based on the previous one. If we were to just define the word recursive, I bet it means based on previous. That would be interesting for someone to look it up and let me know. You can put it in the comments below if you look it up. A recursive formula. So in general, we write a recursive formula by giving the first term and then finding our general term based somehow on the previous term. So we would have one term less, n minus 1, because I have tn, so n minus 1 is one less, and then some sort of operations. Okay, we'll come up with an expression that works for all arithmetic sequences later on once we've had a bit more experience. So here's an example. If Tn is equal to 5 plus n minus 1 times 3, what are the first 5 terms of this sequence? So we could easily find the first 5 terms by doing the math. T is equal to 1 is term 1, so n is equal to 1. That means I'm going to sub in 1 for n. And I get 5. That's also my a value. T2 is equal to 5 plus 2 minus 1. I subbed in 2 for the n value times 3. So I have 5 plus 3 is 8. And I could just keep going like this until I get to the 5th term. 3 minus 1 times 3. 5 plus 2 times 3 is 6, so that's equal to 11. And if we notice, let's start writing down what we have so far. The first 5 terms are 5, 8, 11. And you can see now the common difference is 3. I'm always adding 3. It's very clear. So I can add 3 to get 14, add 3 to get 17, and those are my first 5 terms. I could have also found this 4th term here, T4, by subbing 4 in for n into the general term, but it was just easier to use what we knew. Now we could have also, from the very beginning, just dissected the general term equation, because we know that the value here, since it's written exactly like a plus n minus 1 times d, that this would be a and that this would be d. So we could have started with our a value of 5, our first term, and then d is 3, so we could have just added 3 each time. So that would have worked. But when you're not sure, it doesn't hurt to sub in the values and figure it out algebraically. Okay, let's do another sequence. Okay, so we have these numbers, -2, 0, 2, 4, 6, 8. The first term is -2. So that's our a value. A is equal to -2. It can also be written as T1, but we use an a generally to represent T1 when we put it into the equation. So that's right there, a. What is the common difference? So what are we going up by every time? This is very similar to finding first differences with linear equations. So So we have a common difference of 2. So we can figure out the general formula. Tn is equal to a, which is minus 2, plus n minus 1 times 2. It might be nice to simplify this as well. So let's make some space and simplify. So Tn is equal to minus 2 plus, I'm going to distribute the 2 in 2n minus 2. So I have like terms of minus 2 and minus 2 and a 2n. So I'm going to write 2n minus 4. And that's a nice way to write my general term. Double check. So let's make sure that this makes sense and check a couple of values. So T1 using this equation would give me 2 times 1 minus 4. So that is 2 minus 4 is negative 2. That checks out. That's our first value, T1. Now let's check out T2. So we have 2 times 2 minus 4. So 4 minus 4 is equal to 0. And that was our second term, 0. Great, perfect. Can we come up with a recursive formula for this? It's a good idea to rewrite something if you can't see it. You're more likely to make a mistake if you can't see it. So I'm going to rewrite our sequence here, 4, 6, 8, and so on. So recursive formula, remember we always start by giving the first term for recursive formula. T1 is equal to minus 2. And then how can we make every single term based on the previous term? What are we always doing that's the same? We're always adding 2. So any new term, Tn, can be found by taking the previous term, Tn minus 1, and adding 2. It makes a lot of sense since we're always going up by 2. We find the new value by adding 2. And in general, any recursive formula, we can do the same thing. Tn is equal to Tn minus 1 plus the difference between consecutive terms. So that's our general recursive formula. And with recursive formula, you also have to always give the first term. Okay, so we found the recursive formula here. We could double check by subbing some values in. If I sub in a value of if I sub in a value, say I try to find T2, that might be an easier way to make sense of it, then that means I have T2 minus 1 plus 2. So that means T2 minus 1 is actually T1. T1 is negative 2. If I add 2, I get 0. So this was just a quick check to make sure it works. Great. Okay, our final example. For our final example, if T7 is equal to 53 and T11 is equal to 97, find the 20th term. So we don't really have much information here. Usually they give us a sequence if it's written out as a list. They give us the first term, the second term, we don't have that, the third term, the fourth term, the fifth term, the sixth term, we don't have any of those. Seventh term they gave us, the seventh term is 53. Eighth, ninth, 10th, they didn't give us. 11th, they gave us. Term 11 is 97. And way at the end, they want to know the 20th term. We don't know it. So how could we possibly find the 20th term? We don't have the a value. The formula requires Tn is equal to a plus n minus 1 times d. So this formula, we would need to know a and d. We don't know a, and we don't have two consecutive numbers, so we can't find the common difference. So what we can do is we can sub in what we know and try to see if we can solve for what we don't know. Whenever you don't have an idea of what to do in math, a good strategy is sub in what you know, solve for what you don't know. So T7, well, T7 is equal to 53, so I'm going to put that in. Remember, that's like a dependent variable value, very similar to subbing in a y value. A value we don't know, plus 6d. So I have an equation, but I have two variables. I can't solve that. Let's see what we can do with T11. A plus 11 minus 1d. T11 we know is 97. Okay. So what we do have right now is we do have two equations with two unknowns. That's solvable. In this case, we could use elimination, and it would be very easy to solve this. We could also use substitution, maybe move that 6d over in that first equation, isolate a, and then sub that in. I'm going to use elimination because it's good to practice, the easiest thing in this case, so substitution is usually my favorite for everything though. I'm going to do the second equation minus the first. I'm thinking ahead, and if I do 97 minus 53, I'll get a positive number. The other way around, I'd get a negative, so I'd rather work with positives. So 97 minus 53, 7 minus 3 is 4, 9 minus 5 is 4, so we have 44. A minus a is 0a, that's nice. I just won't write it. And 10 minus 6 is 4d. Oh good, we have multiples of 4 on either side. I'm going to divide both sides by 4, and that isolates d. So now I know d. Am I all done? Not quite. I still don't know a, but I can use that, sub it into one of my equations, and find a. So this is my third equation. I'm going to say sub 3 into 1. Numbers are a little smaller in 1. It'll be a bit less work. Okay, so we have 53 is equal to a plus 6 times 11. 53 minus, so that's 66, minus 66 is equal to a. So we have minus 13 is equal to a. Does that make sense? 13 plus 53 equals 66. Good. So now we have our a value. So we have our general term now that we know a and we know d. That's everything we need to do the equation. So Tn is equal to minus 13 plus n minus 1 times d. D is 11. Okay. Now what was the purpose of this question? It's always nice to look back to the question if you lose direction a little bit. Find the 20th term. So we need to find T20. We just need to sub 20 in for n. T20 is equal to minus 13 plus 19 times 11. If I just estimate this to make sure I get something in the right area, 10 times 20 is 200. It's going to be really close to 200. I could probably do this multiplication in my head. 10 times 19 is 190 plus 1 times 19 Okay, 10 times 19 would be 190. 1 times 19. So I add 20 to that and I would have 110. Take 1 away, 109. So, 209. So I think we have 209 here. And I want to take 13 away from that. If I took 10 away from it, I'd have 199. Take another 3 away, 196. We can double check that. 13 negative plus 19 times 11. 196. Good. Therefore, T20 is equal to 196. Done. So remember what our strategies were in this question? Basically, we subbed in what we knew. We knew little parts of the general term Tn formula. We subbed in what we knew, and then we had two equations with two unknowns. We were able to use elimination to find one of the variables, sub that in, find the other variable, and then we had our general equation. We could find T20. So in general, sub in what you know, solve for what you don't know. What was important about what we learned? Here, we learned that an arithmetic sequence it's an ordered list, and it can be represented by Tn. A term in the list can be represented by Tn is equal to A plus n minus 1 times D, where A is the first term, and D is the common difference. And this whole thing is basically just linear functions that are discrete. We just want the whole number, greater than 0 whole number, possible independent variables, and then we get resulting dependent variables because of that. So just points instead of a continuous line. We could also use a recursive formula. So it's the general term. We can find any term using this formula, or we could use the recursive formula. The first term is equal to A, we always write that, and then we can find all the terms after that by taking the previous term and adding the common difference. Oops, I misspelled difference up there. Difference. And that's the basic concept behind arithmetic sequences.